Right, welcome back. So today we're going to talk about Unit 4. Now Unit 4 is a little different than the first three units that we saw because this is not a programming unit, okay? The whole point of this unit is simply for the students to learn something new about computers. And specifically, they're going to learn about the internet. And of course, they use the internet, they were born in the internet, all that kind of stuff. But they may not actually know how the internet works. That's what this unit is about, okay? So there's kind of two big things that we want them to learn, okay? Now, as always, the material is broken down into labs, but realize that these labs have a lot more in common with like the discussion labs that we saw before. And before we might have seen, say, 4 programming labs and 1 discussion lab. In this unit, they're really all discussion labs, okay? So first thing that we want them to learn is that the whole point about the internet is to provide reliable communication, okay? That's it. That's really what the internet does. It provides reliable communication between computers, okay? So let's break a misconception. It is not the World Wide Web, okay? The internet has been around since, oh my God, the 70s, okay? The World Wide Web, you can argue as to the exact starting points, but most people actually point to 1995. That's when Internet Explorer first burst onto the scene with Windows 95. And okay, so maybe 95 is the right day, maybe 92 is the right day when Mosaic was around. You're talking early 90s. That's when the World Wide Web was born. The internet was in place by that time for well over 20 years, okay? Now, the World Wide Web is a very important application that runs on the internet. You know, it's what a lot of people use it for. But there's lots of different applications. For example, email. Email runs on the internet. It's something that a lot of people do. You can transfer files over the internet using something like FTP, which is an old protocol, maybe something newer like SCP. Doesn't matter. You can transfer files over the internet. You can do phone calls over the internet, okay? That's another application that runs on top of the internet. Because what does the internet give us? Reliable communication. And then you can build all these applications on top, okay? So what exactly do we have there? Honestly, if you want to kind of like look at the internet, what you're going to find is a lot of connected devices, like my laptop, my phone, my tablet, and so on. These are all devices that are connected on the internet. And they communicate using a standard protocol. That protocol is kind of the soft side of the internet. You see the devices, that's the hardware side. Then you can also see how they're exchanging messages. That's the software. Those are the internet protocols, which we'll talk about, okay? So that's what we first kind of thing that we wanted to learn, and it really is just correcting a misconception. It's not the web, okay? Now, let's dig into what we mean by reliable communication. I'm sorry, but a lot of this has to be just building vocabulary, right? These are words that maybe they don't know, maybe they know, but they don't actually know what it means. They just heard them and used them, okay? So one of those is HTML, okay? What exactly is HTML? It stands for Hypertext Markup Language. Hypertext, that's the idea that you have a text that you can click on and it takes you someplace else, you know, like what you do on the web. Markup language, that's just how you write it. You have just a little way of annotating content to say, oh, this is a link, this is an image, and so on, okay? So HTML, Hypertext Markup Language, that's how we write web documents, okay? Now, HTTP, which is the Hypertext Transfer Protocol, okay? HTTP is how do I send an HTML file from here to there, okay? So that's actually what the web browser is using when it talks to a web server. They're communicating via HTTP, and the end result of that is that some resource that's in the server gets transferred to the web browser so it can display it to you, okay? I said some resource that's on the server. How do we actually identify a particular resource, okay? So that's the job of something called a URL, or a Uniform Resource Locator. And it's got several parts, but for example, it's got a protocol part. That's HTTP, right? It's what comes before the colon, HTTP colon, bunch of stuff. That is the protocol. Maybe HTTP will slowly go away and it will get replaced by HTTPS, right? That's a different protocol, which is just like HTTP, but it's encrypted, okay? So HTTPS colon, then a bunch of stuff. That's the protocol part. Now, the second part of a URL is the name of the computer, right? We also call that the domain name, okay? The name of the computer where the resource is hosted at. In this particular example here, that name is bjc.berkeley.edu, okay? That's the domain name. And so you always see a URL has like http:// and then the name of a computer. That's where that goes. That's the domain name. Now, after the name of the computer, then you simply have what, for lack of a better word, is a path or a file name. Okay, that is the name of the resource at that computer. So the computer whose name is bjc.berkeley.edu knows about a particular file called website/privacy.html. So that all those three components put together, that's your URL. And so we want the students to actually understand what a URL is and the components that make up that URL. Okay. Something else we wanted to learn about is IP. IP is the Internet Protocol. I'm sorry, you're also going to see IP in a different context, intellectual property, and we'll do that in the same course, right? So we just have to kind of know by context what we're talking about. So IP, the Internet Protocol, is just simply the way that you can refer to another machine on the Internet. Okay. Now, we've already seen bjc.berkeley.edu. That is the human name of a computer, right? Computers in the Internet also have a number associated with them. That is the IP address, IP as an Internet Protocol. And what IP does is it figures out, how do I get a message from this computer that has this IP address to that computer that has this other IP address, okay? So it kind of figures out how to send the message basically by bouncing it from one computer to another until it gets to its final destination. That's IP routing, okay? Now, the other thing that comes here is something called TCP. TCP is the Transmission Control Protocol, okay? And it's often said as in TCP/IP or TCP/IP. And what we mean by that is it's TCP running on top of an internet that's using IP to communicate from one machine to another, okay? Now, what TCP actually does is it figures how to send a whole bunch of data from one machine to another. IP sends a particular message. TCP can send an entire file, can be megabytes, gigabytes large. And honestly, the way that it does it is it takes that large file, it splits it up into small chunks, which are called packets, and sends each packet using IP to the final destination. Now, there's a little bit of magic, because when it gets to the final destination, you have to reassemble the packets to recreate that large file. That kind of splitting up into pieces, sending, reassembling, that's what TCP is about, okay? So these are, 4 or 5 different protocols that we want the students to understand and to know, and if nothing else, to recognize, okay? So that they see what these things mean, okay? Now, the internet is kind of it's an amazing thing that we've constructed over the last, like I said, 50 years or so. And one of the reasons that it's so amazing is because it is redundant, okay? So you may not notice this all the time because, something goes down on the internet and then you can't reach things, right? And so a lot of it goes down. But it's actually intended from the ground up to be redundant so that it's resilient, so that even if something goes down, the majority of the internet is still operable, okay? In fact, here's a little tidbit. It was kind of invented inside the confines of the Department of Defense, okay? And what they really wanted to do was figure out a way for the generals to communicate in the event of a nuclear war. And so you could imagine that because of the nuclear devastation, lots of communication control centers would go down, and the generals can still communicate to have some kind of a coordinated response. So that's actually the birth of the internet. That's the problem we were trying to solve. What if, specifically the Russians, what if the Russians destroy our communication infrastructure? The generals can still coordinate a response. So if this site goes down, it's no problems because this other one comes back up. So here's kind of the picture you want to see. Let's say that computer is trying to send a message to this computer. Well, it can go this way, or it can go that way, or it can go like that, and so on. So you can see there's lots of ways of sending the message from one place to another. If one computer goes down, the others will recover, right? So that's a really special thing about the internet. Now, the other thing that's special is that it was designed for scale. Lots and lots of computers, lots and lots of devices on the internet. And the only way to manage scale is to actually do something in hierarchically, okay? So here we have some of the addressing, store.parks.ca.gov. And you can see the hierarchy in the name. .gov is at the top. Underneath that is CA, so you can have 50 or however many different states you want to have underneath .gov, okay? And then let's take California. Underneath California, there can be lots of different subdomains is what they're called, but you can think of it as different computer networks, okay? So parks, wildlife could be 2 different subdomains of the California. And then inside parks, you can have lots of stuff like the store, well, maps and so on. Lots of different kinds of subdomains. And you can actually navigate by giving a name that is hierarchical so you can get to the machine that you want. One of the things that's beautiful about that is that you don't have to worry about all of the names of all the computers in the world. I mean, there was a time in the 80s when that's the way we added a machine to the internet. We just sent a file around and said, these are all the computers that we know are connected, and added yours to the end of the file, okay? We don't do that anymore. We can't. There's just too many computers. So instead what we do is we say, look, I'm only going to worry about .gov. You worry about whatever's inside Wyoming Gov, for example, or California Gov. That's somebody else's responsibility. The folks who manage Wyoming.gov can do whatever they want underneath. And they can mirror what California did or make up their own. That's totally decentralized control. That's the way to scale something so that it can be a worldwide web. Okay, now let's focus a little bit on that. The hierarchical stuff on the internet really has two main components. One of those is the human readable names. And for example, uio.edu is the main domain of the University of Wyoming. But there's lots of things underneath that. For example, www.uio.edu is the machine that does the web presence of the University of Wyoming. cs.uio.edu is the computer science subdomain where my machine is at. My machine is oberon.cs.uio.edu. So you see, it's Oberon that's only unique within the cs.uio.edu. And you could imagine that somebody in theater actually chose that same name for their computer. It's okay because they're in a different location. Again, that's the idea of hierarchy, right? IP addresses. Those are the numbers that the computers have to identify themselves with. The computers don't identify themselves using the names. They identify themselves using the numbers, IP addresses, okay? So for instance, you could have 172.26. That happens to be the IP address of the University of Wyoming, kind of the entire subnetwork. Now inside of that, you might find 172.26.1.29, okay? That is the address, the IP address of the main web presence of the computer science department. So that's actually www.cs.uio.edu. Its IP address is 172.26.129. There could be another machine, 172.26. That means it's in the University of Wyoming domain, right? .2.47. I don't know what that machine is. I just picked it at random, okay? But the whole point is that every machine inside University of Wyoming might start with 172.26, okay? So we have two different hierarchies here. Now, be a little bit careful. The hierarchies in the domain names, in the human readable names, go from least to greatest. So it is www, that's the least part, uio, edu. uio is all of the University of Wyoming. Edu is all universities. So you see, we're going from smallest to biggest, right? IP addresses go the other way around. 172.26, that's University of Wyoming. And then you dive in, 172.26.1.29, okay? So it's a little bit strange in that sense, okay? But they're both hierarchies. One goes left to right, the other one goes right to left. Why? I don't know, okay? That's just the way somebody picked it, okay? And they got to choose, and that's what it is. Now, humans think about machines using their name. Machines think about machines using their number. There's actually a way to convert from one to another, and it is one of those applications that runs on top of the internet, okay? It's called the Domain Name Server Protocol, DNS, okay? And it just converts names to IP addresses. So I can talk about www.uio.edu, and the DNS server will tell me, oh, that's this number, okay? So that my computer can talk to it. Okay, what we're doing is we're connecting computers and devices all over the world. So the thing that makes that happens is a particular kind of device called a router, okay? And the students need to understand, roughly speaking, what a router is, okay? Now the good news is that routers are actually fairly simple. You can almost think of them as intersections on the highways, right? So when you have an intersection, that's one way to go from, say, I-80 to I-25, okay? You can just go, you're in this I-80 network, and you at the intersection you get off, and then you join the I-25 network, okay? That's what a router does. So a router is basically in both networks at the same time. And it takes messages that are going in one network and passes them to the other network when it's necessary. So if I want to talk to a computer that's on a different network, I'm in the computer science network at the University of Wyoming, but I would like to talk to somebody in, say, biology at the University of Wyoming, then there is a router that is actually connects traffic from the computer science network to the biology network, right? And of course, eventually there's a router that connects the University of Wyoming to the outside world, right? And so that router might actually go to an ISP. It's in both networks simultaneously, the ISP's network and the University of Wyoming network. Traffic that goes outside will go through that router. Okay. The other thing they need to kind of appreciate is that IP, the Internet Protocol, which is what understands things like routers and networks, has had different versions. And the version that is, I would almost say, dominant in the Internet today and has been for the last 20 years is IP version 4 or IPv4. Okay, that's the one that has addresses like 192.9.200.5, right? 4 small numbers between 0 and 255 connected by dots. Okay, IPv6 is a much larger address space. Okay, so IPv4 is being replaced right now by IPv6 for a very simple reason. In IPv4, you only have 4 small numbers to make up an address, and we're running out of addresses. There's too many computers plugged into the internet, so we need more than just 4 small numbers. IPv6 actually has something like 8 small numbers that it can use. It's plenty. It's plenty. IPv6 will take care of the problem for many years to come. It hasn't been completely rolled out. Okay, my computer understands both, but most of the time it's speaking IPv4 because that's what all the other computers are doing. Ironically, I think all of them pretty much now understand both, but we're still in that transition period, so they're like, well, I'll just talk IPv4 because that's what I know everybody else can understand. And so we just haven't made the flip of the switch to move to the new protocol, okay? But your students will understand that there's 2 different protocols and why we want to go from v4 to v6. We run out of v4 addresses, right? That's the entire mystery. Okay, something else that's really important in the internet is what's called packet switching, okay? And again, your students need to understand this little concept. And honestly, there's not that much to the concept, but you see, IP transfers one block of data to another computer. That's what it does. We call that little bit of data a packet, okay? So IP transfer packets from one computer to another. TCP, that goes on top of IP, then what it does, it takes a very large amount of information, breaks it down into smaller packets, and transfers them using IP. Now, the big thing that we want the students to appreciate is that IP does not guarantee delivery. It's a best effort kind of thing. So when you go and transfer a packet using IP, you say, I would like machine XYZ to get this information. And IP says, okay, I'll give it a shot. And he tries to send it from one router to another. And if it doesn't get there, he goes, I tried. What do you expect, perfection? That's okay a lot of the time, okay? So it is an unreliable protocol. It may or may not make it all the way. TCP adds reliability, okay? So not only does it split a large file into small packets, it actually adds reliability. So that let's say that it has to send 50 packets from machine A to machine B to transfer a file. It actually says, this is packet 1, this is packet 2, this is packet 3, and it waits to hear back. I got packet 1, I got packet 2, I got packet 3, okay? By the way, it could come in a different order. I got packet 3, then I got packet 1, then packet 2. It's okay because they can reassemble them in the proper order, right? They don't have to get there in the same order. And in fact, remember that there's multiple routes. So it could be that it decides to go in 2 different ways and one of those is backed up, so it takes a little longer. That's not a problem. It'll eventually, all the packets get there and then they get reassembled into the file. But what can happen is that packet 3, for example, may get lost. It just never ends up at the destination. So at that point, what the first machine will be, machine A, will be to resend packet 3 to machine B and says, hey, this is that packet that you never told me you got it, and it's really important that you have it, so here it is. B doesn't reassemble the entire file until it gets all the packets, right? And A will resend any packets that it doesn't hear about. I got it, I got this one, I got that one. So using that kind of technique, TCP actually does guarantee that the file will eventually get transferred. even though IP does not give any such guarantees, right? So this is kind of a way to build reliable communication on top of an unreliable foundation. It's amazing that this works, but TCP is what everything else is built on top of. Like, for example, HTTP is using TCP protocol to send data back and forth, okay? So some of this stuff is actually kind of made easier to understand, easier to grasp by the unit because they actually build a little lab that shows how a message can be broken down into packets. It's really not a programming lab so much as a look how this works. So just kind of to remind the students that this is a computer science course and there's the computer science part, so to speak, okay? All right, protocols, okay? The entire internet is built on top of protocols. And there's lots of these, right? So at the very least, we wanted to understand that there's different kinds of protocols. So for example, there's what are known as application protocols. And these are made up by developers, by computer scientists that kind of want to use the internet as it exists, all the TCP/IP infrastructure, and build something on top of it. Like, wouldn't it be nice if we could exchange documents that you could click on, and that's HTTP. Wouldn't it be nice if you could ask me the name of you give me the name of a computer and ask me for its number? That way you don't have to know the numbers of all computers. Well, that was DNS, right? SMTP, I would like to send you email. That's what SMTP is, okay? IMAP, I would like to read my email. That's what IMAP is. It's a different protocol for sending than for reading your email. There's lots of protocols, okay? How can I send network phone, right? Phone calls over the internet. How can I send video over the internet? How can I stream a movie over the internet? All of those have specialized protocols, okay? Those protocols are built on top of the transport layer, and the transport layer is what actually says, I know how to send stuff from here to there. I already mentioned TCP, okay? Another layer, which is kind of at the same level of TCP, is called UDP. And the thing about UDP is that it's really, really blindingly fast, okay? But it doesn't guarantee that the packets get there, right? So it's actually ideal for things like streaming. So you might lose a little bit of packets in the middle, but that's all right because it just picks up again and then off it goes, right? Gaming protocols. You want the fastest possible communication between the gamers so that when somebody shoots, somebody else feels it. Okay, so if a few messages get lost, it's not that big a deal. UDP is perfect for that. Okay, so again, trade-offs. Okay, underneath that is the actual internet layer protocols. Those are ones that say here is one packet that goes from here to there. That's IP, right? So that's where the IP protocol goes. Now underneath IP is all of the actual hardware protocols that make one computer communicate with another computer, just at the level of ones and zeros. Okay, and so we have, for example, Ethernet. That's when they're communicating over a wire, right? You might see something that looks like a phone cable, which is an RJ45 wire that plugs into a special device on the other end, and that actually does communication, right? It's kind of the typical wired communication of these days. You can also have Wi-Fi. Like my laptop is running on Wi-Fi right now, and it connects to something else over radio waves, okay? So that's a different way of sending zeros and ones across I still say across the wire, even if we're talking wireless communication, okay? Another way is my phone is connected to the internet. Right now, I'm at the University of Wyoming, so it's actually hooked up to the University of Wyoming Wi-Fi radio connectors. But when I'm not around here, it can actually communicate by going to the cellular phone network, right? So the cellular system actually is another way of exchanging ones and zeros. That's all the way down at the hardware level. It's called the link protocols, all right? Okay, so Lab 2, again, is it's even less technical, but it's very important from the social aspect. And it talks about communication protocols. And one of the key questions is, how do we agree on what the protocol is? What keeps the internet from one group going one way and another group going another way, and then their stuff can't interoperate, okay? And the answer is that there is one standards body that kind of articulates and governs what the protocol should be. And that body, because of historical reasons, was actually based in the United States. And so it was the United States who controlled kind of the internet for the entire world. You can see vestiges of that. For example, Coca-Cola in the US is Coke.com, right? .com means it's a company. Coke is the name of the company, right? But if you go over to, say, England, right? they don't start in .com, or I should say they don't end in .com, because all of those kind of unique addresses are for US companies. In England, they end in .uk. And then underneath that, it might be .co, co for company instead of com. Hey, you can do whatever you want, right? That's the whole point. And then is Coke, so it'll be coke.co.uk. What can they just say .co instead of .uk? Because it was the US who set this up, and they chose the top level domains for themselves. Why not, right? I mean, what else would you do? So yeah, the US has kind of a disproportionate amount of influence on the internet. It was also born here, so you can argue that. All right. By the way, that is false as of very recently. The US actually did give up control of the internet, gave it to an international body, and I think that was the right thing to do. Okay. Now, part of the background of that, of course, is NSA, right? And looking at data that goes across the wire. A lot of this was released by Mr. Snowden back there, who's well, he needs to shave, but anyway, he's over there, and he did a lot of the stuff having to do with, hey guys, you need to be careful about what the United States is doing through internet traffic, and that's going on. So that's actually part of kind of the background of the discussion in this unit, rather this lab. And why are there unit open protocols? Why do we care if they're open or if they're owned by, say, Facebook, which of course would never dream of using your data for its own advantage? So those are the kinds of things that this lab is all about. Okay. Now, the next lab is again mostly non-technical, or there's a little bit of technical stuff in it, and it has to do with cybersecurity, and the focus, at least in the beginning, is on encryption. Okay. So encryption is one of the solutions in cybersecurity, because if there's no way for you to read a message that I sent to somebody else, then there's fewer things that you can do to kind of interfere with that message or exploit the information in that message. Okay, so there's two kinds of encryption. There's something that goes by the name of symmetric cryptography or symmetric encryption, and the idea in there is that the two people who want to communicate, okay, in encryption, and it's traditional to call them Alice and Bob. Okay, but if Alice and Bob want to communicate, they have to have a secret that they share and that nobody else knows, okay? And that secret is used to encode a message, and it's also used to decode the message. So for example, one of the first people who did this was Caesar, okay? Julius Caesar. He was invading the Britons, and he needs to be able to communicate with his generals. So what he did is he came up with the idea of a cipher. And the cipher, you can actually see down here, is really very common. So for example, instead of writing an A, he might write a T. Instead of writing a B, he writes a U. Instead of a C, he writes a V, and so on. An even more general cipher is called a substitution cipher. Instead of an A is something. Instead of a B is something. And we just agree on what that somethings are. The Caesar cipher is even simpler, because what we have to agree on is by how much do we shift the letters. Once I know that A goes to a T, B has to go to U, C has to go to V, and so on. Okay, it's fixed because it's just by how much am I shifting. Okay, this was actually perfectly reasonable in the time of Caesar. Today, a computer can crack that code in less than a millisecond, probably. It just goes, oh yeah, you shifted by this much. Even if it's a complete substitution cipher, where you can exploit the fact that once you know what one letter is, you know all of them. Okay, even if it's slightly more general than that, it can still break it in less than a second. And the reason is there's too much statistics involved in the letters. E is very common, so it just goes, what letter appears most commonly? I'm betting that's an E. And before you know it, it's broken the entire thing. Okay.